Okay, let's talk more about some Riemann sums. So far we've kind of got the upper integral and the lower integral, and when those two get close together, they converge. So let's review that real quick. So the lower integral, the picture, if I want the sum here from a to b, L of a certain partition of f on AB, I break this into rectangles. It doesn't matter necessarily how wide or close together these things are. And the lower part, remember, means that I find the lowest point in each of these subintervals to draw the height of the rectangle. Alright, so this is definitely going to be under the area of the curve, because each of these rectangles that we've drawn has a smaller area than the area under the curve, right? I've got this, 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 and so on. There. And I've picked the lowest points, which it looks like that. Maybe that one's in there. Maybe this looks here, 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 and so on. The upper sum, this is the minimum points so mi equals the minimum of f on the xi to xi plus 1 interval, and this is going to be the sum of mi times xi plus 1 minus xi from I equals 0 up into n, or however big your partition is. Okay, so that was the lower. It's a lower estimate for the integral, and that lower estimate is quite a ways off, right? The error of this estimate would be all the stuff that's above these triangle or rectangles, but still inside the curve. All right, I want to know the area under the curve. This lower Riemann sum is an estimate for that, but it's off by this purple stuff. Okay, similarly, we could do this with an upper integral, and the picture for that, I've got this function. I'm going from a to b again. We take another partition. Maybe that's our partition, and I draw rectangles, and I want the maximum values now instead of the minimum values. So the rectangles I draw, they're above the curve. And so they overestimate the area under the curve here. Okay, and this would be, this green area overestimates the area under the curve, but not by too much. And that's going to be the upper Riemann integral on that partition, and we find that by, let's set capital Mi equal to the max of f on the interval xi plus 1, and then this is equal to, this upper integral is equal to the sum from I equals 0 to probably n minus 1 so that I don't count an empty integral over here, of capital MI times xi plus 1 minus xi, which is, this is the width of each rectangle and this is the height. So width times height is area, and adding up a bunch of areas is just going to give me another area. Okay, this one overestimates the area under the curve by a little bit, by these little purple areas here. I've got these sort of almost triangular shaped pieces that we've overestimated the area by. That purple area is an overestimation. As your partitions got finer and finer, these overestimations and underestimations got smaller and smaller for Riemann integrable functions, and we were able to compute what the actual area is by looking at the supremum of the lower guys, what's the biggest that a lower integral could be, versus the infimum of the upper guys, what's the smallest the overestimates could be, and that if they matched, we said the function was integrable. Okay, so let's see how Riemann sums, other Riemann sums, other ways to do this instead of just lower and upper. A lot of textbooks have like a left-handed sum or a right-handed sum, because those are easier to calculate, and their errors are going to fall somewhere in between the error from the upper and the error from the lower. So let's look at left-hand Riemann sums. What do I mean by left hand? Well, the picture, it's similar again. I've got from A to B, and usually textbooks have you form an easy partition to work with. The easy partition being something that is spread out uniformly so that each of these rectangles have the exact same width. Okay, so I take the width here, xi plus 1 minus xi is equal to b minus a over n for all I. Sort of a uniform width or uniform gauge partition. And then how I form the rectangles is, well, I just look at the left-handed point and draw my rectangle from that left-hand point. That's going to be where the top of my rectangles are. Okay, and I don't get one at B, but all the other rectangles, they're either overestimates or underestimates. Some of them are under, some of them are over, right? And my error is going to be, well, I have to subtract, or I have to be off. I'm too small by this amount, I'm too big by this amount, too big by this amount, too big by this amount, too small, that's probably too big in that middle area, too small, too small, too small, too small. And so you put a signed difference, and that's going to be your error. But the formula for these is sort of nice, because I can actually use f at specific points from the partition. I don't have to figure out where the minimums and the maximums are in each of those intervals. So I can actually compute these Riemann sums fairly quickly and not have to deal with maximizing or minimizing functions on an interval. So let's write down what that left-hand sum is. Left-hand Riemann sum is, it's the sum from I equals 0 to n minus 1. Well, let's say that delta x is equal to this b minus a over n. That's how much the x value changes for each of these intervals. This is delta x here. Each one of these little lengths is delta x. Delta x again, delta x, and so on. So what we do is it's just delta x is the width of each of the rectangles, and the height of the rectangles is the function value at the left-hand side. So I'm going to look at a plus I times delta x. So if I is 0, I evaluate the function at a, and I get this point. This is f of a plus 0 times delta I. This guy right here is f of a plus delta I, or delta x. This one is f of a plus 2 delta x, and so on. So I can actually kind of compute these with no problem if I know the function formula. I can just plug in these values on each of the points and get that computation, rather than finding the minimums and the maximums. And this is sort of a better estimate in some sense than the lower or the upper, because, well, this sort of, it's halfway between the lower and the upper when the function's not monotonic, right? If the function's in this area, right, where the function is increasing, I'm going to be underestimating. This is an underestimation when the function is increasing, and over here we've got an overestimation when the function is decreasing. F is decreasing. Okay. So it sort of combines a little bit of an overestimate and a little bit of an underestimate, and those balance out to be somewhere in the middle. We can do this also with the right-hand side. So the picture on the right-hand side is going to be similar. Got this function. Here's a to b. We take a uniform partition again, where each of these widths is delta x equals b minus a over n, however many pieces in the partition you want. Then the right-hand Riemann sum. Well, where do I want my heights drawn? I want to start here at the right-hand side to draw my rectangles. Right-hand side, right-hand side, right-hand side, and so on. And this is sort of the opposite. When this function is increasing, I've got an overestimate. When increasing, I've got an underestimate when decreasing. But again, it sort of balances out. It's somewhere between the upper estimate and the lower estimate. It's somewhere in the middle there. So this is also a good estimate, because when it's Riemann summable, if this lies between the upper sum and the lower sum, it's going to get sandwiched into that actual integral. So let's write down the actual form for this right-hand Riemann sum. Okay, so I'm going to be doing delta x again for the widths. And where am I evaluating? I'm evaluating at a plus I delta x again. But now the first place I evaluate is when I equals 1, and it ends at I equals n. So it's pretty much exactly the same sum that we computed before, only where do I start my summation? Do I start it at 0 and end at n minus 1, or do I start at 1 and end at n? Okay. So this is my right-hand Riemann sum. And I didn't show you before, but since this delta x is constant, you can pull that delta x out front and just take the sum from I equals 1 to n of f of a plus I delta x. Okay. Alright, so that's a right-hand sum and a left-hand sum, and they're both good. But they're both kind of off. We could probably get a better estimate if we look at this picture. I can maybe get a better estimate if I draw this triangle in here instead of looking at the left-hand or the right-hand sum. If I look at the triangle, I can get this sort of trapezoidal area estimate for each of these. Okay, and then I can get this trapezoidal estimate for this one, and so on. And that's going to give me a better estimate yet for the area under this curve by using these trapezoids. Well, let's look at one of these rectangles real quick. If I can look at this guy. Sort of the green estimate is the right-hand sum, and the purple estimate on this rectangle, let's focus on this guy right here. The green rectangle is the right-hand sum. The purple estimate here is the left-hand sum, and the trapezoid would be halfway between them, right? If I look at this trapezoid here, it's halfway between the green estimate and the purple estimate. So what I could do is I can add the right-hand sum and the left-hand sum together and divide by 2, because that's going to add each of the over estimates plus each of the under estimates and then divide them by 2. So that's our trapezoid rule. And that's going to be a better estimate yet. Let's draw a picture for that. Okay. So we've got this. We can go from A to B with an estimate. We have a uniform partition. And I'm going to take my left-hand estimates. These are going to be my left-hand estimates, or the green ones. And we'll take the right-hand estimates, which are the purple ones. And let's kind of fill in those guys there. Okay, so these give me two rectangular estimates, and yeah, let's go orange. If I want this trapezoidal estimate, I'm going to take the green rectangle plus the purple rectangle and divide by 2, and that'll give me the orange trapezoid's area. Not sure which one's higher on that one. That one's fairly even. And then this guy here. Okay, so the orange trapezoid sum is going to equal, well, they're still delta x again in width. Everyone is delta x. You can start at I equals 0 or 1, either one. It depends on what we're going to put in the functions. So the right hand side is f of a plus I plus 1 delta x, right? Plus f of a plus I delta x. And then I want to divide by 2, but since each of those is divided by 2, I can do the divide by 2 out front. Okay, so let me kind of label what's going on with this. This is the width. This is the height for the right-hand side, right-hand sum. This is the height for the left-hand Riemann sum. I should say right-hand Riemann sum. And then when you add them together and divide by 2, you take the average. And that's sort of your formula for the area of a trapezoid, right? You take if you have a trapezoid, even if it's a right trapezoid here, you take this length plus this length, divide it by 2, and multiply by the height. So this would be delta x here, and the average of a and b is this stuff inside the summation. And you get one of those rectangles, or one of those trapezoids, for every I value from 0 to n minus 1. Okay, and this is a better estimate yet because it's halfway between the upper sum and the lower sum. It's exactly halfway between the left-hand sum and the right-hand sum, but each of those are between the lower and the upper, so this is sort of a better estimate yet. And some texts go into better and better approximations and use sort of weighted averages of maybe 2 of the rectangles or things like this. Like, so if I was trying to find this area, what I could maybe do is I can break this into a partition, equal sizes, and we can sort of get good estimates using something called Simpsons Rule, or otherwise, where, well, let's look at this guy, and let's look at sort of this guy right down here, sort of to take the middle guy and draw a tangent line, and you get this rectangle, and take the 2 endpoints there, and you get the average here. And if you add that up, and then you do the same thing for these guys and take the average of the middle, you add that up, then you do it here and you take the average in the middle and add that up. Each of these interior rectangles gets added in twice to the area, so you divide everything by 2 and then you add this rectangle and this rectangle again, and you get a good estimate for what's under the curve, and it's sort of better than the others, and so on. And there's more and more sophisticated ways that you can approximate these areas, but the simpler ones that are easy to compute are the left-hand sum, the right-hand sum, and the trapezoid rule.